In this video, we will introduce the concept of a related rates problem. So let's start off with the following motivating example. A small balloon is released at a point 150 feet away from an observer who is on level ground. If the balloon goes straight up at a rate of 8 feet per second, how fast is the distance from the observer to the balloon increasing when the balloon is 50 feet high? So let me go ahead and draw a picture representing this situation. So we have an observer who's 150 feet away from where a balloon is released, and after some time the balloon is going to have a certain height, let's call it h, so this is our balloon, and the balloon is going to be some distance away from the observer. Let's call that distance big D. And let's think about what information is given to us in this problem. So we are letting h be the height that the balloon is from the ground, and big D being the distance that the balloon is away from the observer, and this information, is put in here in terms of this right triangle. So the question that I always try to think about first is, what do I know and what do I want to find? So the information I know in this problem is that the balloon goes straight up at a rate of 8 feet per second. A rate of. So a rate of change is a derivative. So what they are telling us is the rate of change, dh dt, is equal to 8 feet per second. And in these related rates problem, there will be a rate of change they give us, and there will be a rate of change that we want to find. So what rate of change do I want to find? Well, I want to know how fast is the distance from the observer to the balloon increasing when the balloon is 50 feet high. So how quickly is this rate of change? So find the derivative of big D with respect to t, and we want to find this when the height of the balloon is 50. So now that we've drawn a picture and kind of encoded all of the relevant information that we can in the picture, we've written down the rate of change that is given to us and the rate of change that we would like to find. So what we need to do is find some equation relating D and H. And looking at the triangle, a relationship that jumps out to us is the Pythagorean theorem. We know that d squared is equal to h squared plus 150 squared. And when doing these related rates problems, what we would like to do is somehow go from this equation relating the variables to getting an equation involving the various rates of change. Well, how we can get these is by implicitly differentiating both sides of the equation with respect to t. So differentiate with respect to t on the left and on the right. And when we do so, remember that the quantity d and the quantity h are both varying with respect to t. So on the left, by implicit differentiation, we get 2 big D times the derivative of big D with respect to t. On the right, we get from the implicit derivative of h squared 2h times dh dt, and the derivative of a constant, 150 squared, is just 0. So we want to know what is d big D dt. So I want to algebraically isolate for this quantity. So this rate of change that we would like to know, well, we can cancel off the 2, which is on both sides, and we'll have h over d dh dt. And what we would like to know is specifically what is the value of this rate of change when h is equal to 50. And if I think about plugging in, well, I can plug in directly h equals 50. We know from the given information that dh dt is 8 feet per second. So I can multiply this by 8, where the DHTT is. But a common part of the problem is we're now going to have to find the value of D when H is 50. But if we go back and look at our relationship between H and D, the Pythagorean theorem, this is something that we can easily solve for. So let's kind of do this as just a small side problem. When H is equal to 50, we have D squared is 50 squared plus 150 squared, which tells us that D is going to be the positive square root of 50 squared plus 150 squared, which is going to be equal to 50 square roots of 10. And what we are going to do is take this number for D and just plug it in. So we will plug in 50 square roots of 10. The 50 in the top and the bottom cancel out, and the desired rate of change that we are looking for is 8 over square root 10. And we should always give units here. This is a rate of change of the distance, so it would be feet per second. Now, let's look at this from a big picture, maybe more procedural perspective, and think about the approach that we have taken. We read the problem carefully. We drew a picture and we encoded it with all of the information that we could. We've written down the rate of change given, the rate of change that we would like to find. We related them together via an equation. We differentiated implicitly, and then we solved for that desired rate of change. Now, in general, these are the exact guidelines that we would follow to solve any related rates problems. Read the problem carefully. And it may sound silly to write that down, but really that's one of the most important things, to read the problem as carefully as possible. Draw a picture and introduce notation. That is, variables that represent things like, say, the distance from the balloon to the observer, the distance from the ground to the balloon. And for those things that we're introducing notation for, we're assigning symbols to all of the quantities that are functions of time. We had big D and H. State the rate of change you know and the rate of change you want to find. Then we write down an equation relating those quantities, implicitly differentiate with respect to x, and we substitute in that known information to solve for the unknown rate. So let's look at one more very typical example. So another very typical related rates problem. Car A is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour. Both are headed for the intersection of two roads. So kind of a visual of this, a picture we want to draw. We have car A and we have car B. Car A is traveling west, car B is traveling north, and they're heading for this common intersection. Okay. At what rate are the cars approaching each other when A is 0.3 and car B is 0.4 miles from the intersection? So we want to know the rate at which the cars are approaching each other. So what we need to think about is how far apart are they? So if we draw in the hypotenuse of this triangle and maybe call that distance C, then the rate of change dc dt will be telling us how quickly the cars are approaching each other. So we want to think about what rates of change we know and what rate of change we would like to find. So we said we want to find dc dt at that specific moment when car A is 0.3 miles and car B is 0.4 miles from the intersection. So we need to introduce some more notation. We will use little a to represent how far car A is from the intersection, and little b to represent how far car B is from the intersection. So we want to find dc dt when little a is 0.3 and little b is 0.4. And what rates of change do we know? Well, we know how quickly car A is moving and how quickly car B is moving. So we know d little a dt and d little b dt. And here we have to be careful. Car A is traveling west at 50 miles per hour. So the gut instinct here is to just write down, 50 miles per hour. But we have to think about what little a is representing, the distance between car A and the intersection. So that distance is decreasing, which means the rate of change should be negative 50 miles per hour. We use a negative sign when we have a decreasing rate of change. Likewise, dB dt is minus 60 miles per hour. So we've drawn a picture representing the situation, labeled all of the quantities that vary with respect to time. We've written down the rates of change that we know, the rate of change that we would like to find. Now we need to write down an equation relating together the A, B, and C. But hopefully we can very clearly see what that equation is going to be looking at the triangle. Once again, it's just the Pythagorean theorem. A squared plus B squared is equal to C squared. And now that we have this equation, we simply differentiate both sides implicitly with respect to t. And A, B, and C all depend upon t, so we have three implicit derivatives. So 2a dA dt plus 2b dB dt equals 2c dC dt. Now the first simplification is each term contains a 2, so we can go ahead and cancel that off. And then we think the quantity we want to find is dC dt. So we can go ahead and isolate that dC dt. dC dt will be equal to A dA dt plus B dB dt, and then we need to divide everything by C. And what we would like to determine here is what is the value of dC dt when A is equal to 0.3 and B is equal to 0.4. So we need to plug these values in. And additionally, not only do we know, what the A and the B are going to become, we know dA dt and dB dt. They're the given rates of change. But before we are able to completely solve for dC dt, we need to determine what is C. So when A is 0.3 and B is 0.4, what is C? We go back to this Pythagorean theorem. So just know, kind of a side problem here, we have A squared plus B squared is equal to C squared. So 0.3 squared plus 0.4 squared is equal to C squared. So 0.25 squared is C squared. And C is going to be 0.5. And we can now plug in all of these values. So we have 0.3 for A, dA dt is minus 50, plus B is 0.4, dB dt is minus 60, and this is all divided by C, which is 0.5. And if you go ahead and plug this into a calculator, what you will get back is minus 78, and the units to go with this in this problem, it's a rate of change of distance, so minus 78 miles per hour. Once again, from this big picture perspective, we've read the problem, drawn a picture representing the situation, and labeled all quantities that are varying with respect to t. We've written down the rates of change that we know, the rate of change we wish to find. Found an equation relating them, implicitly differentiated, solved for the rate of change we want to find, and we've plugged in that given information.